Hello, everybody. Welcome to the last part of, I think, section 3B here. All right. So we talked about the null space, we talk about the range, we talk about the injective, we talk about the surjective, and then we also talk about the fundamental theorem of linear maps, the corollaries. All right. So in this last recording here, we're trying to see the connection between what we have learned, especially those two corollaries, and put that into a context of the linear algebra, which hopefully everyone already learned at some point and still remember something. All right. So we're going to go over a general discussion, but I think it's not hard to think about some specific cases, like if you have a matrix equation or a system of linear equations with 3 variables, 5 equations, or 10 variables, 3 equations, what's going to happen? All right, so that's actually something we're going to try to talk about here in a more general discussion here. All right, but write down some specific cases will help you better understand notation here and better understand the conclusion here. All right, so I already wrote 2 lines here saying, let's define an operator or a map from the Fn. All right, so this is the over the field, all right, and then their dimension is n here to the Fm. All right, so remember this book is pretty consistent with putting the n in first and then the m second. All right, and we'll see why is that. All right, and then the way we define this map is a t of x sub 1, x sub 2, x sub n. So the input is a vector, any vector with n coordinates. And the output must be in Fm, right? So in other words, you want to have the output to be a vector with m coordinates. So that's exactly what's happening here. And each coordinate is a combination of the input vector about this x1 up to xn, right? So if you look at the first sigma notation here, the a sub 1 k comma k, the 1 indicate this is all this a will contribute to make the first coordinate in Fm, all right? And the last one is a sub m comma k, so the m indicate all this a sub m something will make the contribution to the last the m's coordinate in the Fm, right? And then since each one is coming by the combination of the x1 up to xn, so really each x need to have a number in front of it. All right, so this k which is changing is from 1 to it's not from. I think I make a typo here. This k, each one is from 1 to n. All right, that's absolutely wrong. Not infinity to n here. All right, so to n here. All right, so then that is the a11 times x1 and a12 times x2 and then a1n times xn. So they use every x coordinate and you add all this together. That's only give you the first y1 in the Fn. Right, so the last one is a1, so am1 times x1, am2 times x2, up to amn times xn. Then altogether give you the last one, the y sub m in the Fm. All right, so that's how this works. And then if we consider an equation here, of course, you can probably, I don't know if the book does that or not, probably not, but if you're familiar with the linear algebra, so you realize what we did here is we use a11, a12, up to a1n to match with the x1, x2, up to xn, right? So this row dot with this column will give you the first one, and then you use the a21, a22, up to a2n, right? So then that's each one, a21 match x1, a22 match x2, and so on. So that's give you the second coordinate in the resulting vector. And then the last one, this is am1, am2, up to amn, and then this match those entries in x vector, and then this give you the last one in the y, right? So then this is a m by n matrix, and then this n by 1, so you finish with n m by 1. All right, so that's why the this T is from Fn to Fm. The n go first, m go second. But when you matrix, the matrix is m by n matrix. For instance, if T is from F2 from R2 to R5, your matrix is a 5 by 2 matrix. All right. So then we consider two questions here. All right. We consider two things and two questions, and we put some congruence. So first, let's consider this Tx equal to 0, or x is the vector, 0 is the vector in the other side. So this is equivalent to the homogeneous equations. Homogeneous equations have different definitions according to context, and in this homogeneous equations, we mean the 0 on the right-hand side. All right. Xk here. All right. So this equivalent to this system of homogeneous equations. And this is in the sigma notation. All right. So if you want, you can write this. It's probably even better either to see this in the expanded form, like A11, we said, times x1, all right, up to the last one is A1, and then there are n, so xn, right, is equal to 0, and then this is am1 x1, and then up to amn xn equal to 0. So then in this system, all right, so there are how many equations we have here, right? So from 1 to m, so there are m equations, all right, and how many variables? When we say variables, how many different x values here? Well, there are n variables. Right? So of course, when you take all the x values to be 0, for any homogeneous system, 0 is always a solution, right? So then the more interesting question is, do we have a non-zero solution to this equation? All right. So then the question we ask here is, does this homogeneous system have a non-zero solution? Sometimes if you look at the linear algebra textbooks, they call 0 because it's automatically is a solution. It's called a trivial solution. So we're looking for the non-trivial solutions to this, right? So how do you know whether there is a non-trivial solution or not, right? Well, if you look at the abstract form, Tx equal to 0, right? So then that means this Tx equal to 0 has a non-zero solution, right? And then, well, Tx equal to 0 has a non-zero solution means the null space of T is not just equal to 0. There must be at least another non-zero vector there in the null T, right? In the null T. So then this means the dimension of the null T actually is greater than 0. Because if it's equal to 0, that means it's only containing 0. If that's otherwise, then these two things not equal to dimension, null T bigger than 0, and the null T is non-trivial equivalent, right? And what can we say from here? Well, by the fundamental theorem of the linear maps, we know the dimension of V is the dimension of the null T, and then plus the dimension of the range T here, right? And then this one here, in such a case, this is the dimension of the F. Remember, the T is from, again, remind everyone, T is from Fn to Fm, right? So this is the dimension of, according to the context for this particular question, this dimension of n, so this is dimension of Fn, which is equal to n here, right? And so the dimension of null T is the n minus the dimension of the range T. But the dimension of the range T can never go over the dimension of the W. Well, the W here is the F M, all right? So then this is greater than or equal to n minus m. So under what sufficient condition we guarantee this system has a non-trivial solution? Well, if this n is strictly greater than m, all right? For example, if you have from the R5 to R2, or if you from R7 to R6 or something like that, if your linear map constructed that way, then the dimension of null T is strictly greater than 0, and then that implies the homogeneous system, right, has non-trivial solutions or has non-zero solutions. All right. So our conclusion is right here for the first case is our conclusion is a homogeneous system. I will use plain language here. A homogeneous system of linear equations, right, in which there are more, because what is the n and what is the m here, right? So if you go back to look at what we did here, m is the number of the equations, n is the number of the variables, right? So there are more variables than equations. For instance, if you have 5 variables and 3 equations, then this kind of system must have non-zero solutions. That's our conclusion. All right. So for example, as we said, right, if you have something like a 3x1 plus 2x2 minus 7x3 is equal to 0, and then negative x1 plus 5x2 plus 10x3 is equal to 0. If you have something like this, if there are 3 variables, right, and greater than 2, there are 2 equations here, all right, then this system, this homogeneous system, must have non-zero solutions. Of course, if x1, 2, 3 are all equal to 0, then it's always a solution, but there's something else. So that's so one application is originally from the fundamental theorem of linear maps, but that's actually the corollary. I forgot the one of the 2 corollaries we did there, right? So this one is to talk about the the first corollary we proved in the previous recording, right? Dimension of the V is greater than dimension of the W, so there's no injective map. All right, so there must be something more to go to 0, not just 0 goes to 0, something else goes to 0. All right, so that's one case. Now the second question we want to study is, it's the same notation, the same system, but the second question is we consider the equation not a homogeneous equation, but a T of x equal to a C, where the C is any vector in the Fm, T is still from Fn to Fm here. All right, so then we can write this into a system of equations. So I'm still going to use the sigma notation and the expanded. So still k from 1 to n. You have this, we still use a here, a is 1k, 2xk equal to c1, or c1 is the first component, and then k from 1 to n are amk, xk equal to c sub m, or equivalently, this is the a11, a11 x1 up to a1 n xn, because x is in fn here, right? So c1, and then am1 am1 x1 up to amn xn is equal to c sub m, right? So our question for this is, for NAC, does there always exist at least one x such that Tx is equal to C, right? Well, the conclusion is actually we're trying to say is no, right? Because what we're saying is, well, under a certain circumstance between these two dimensions, and then actually the answer is there always at least a choice for the C such that that system of equation is inconsistent. There's no solution, all right? So that's where we want to end up with, all right? So remember, for any, if we have this case, for any C in Fm, there exists x in Fn such that the Tx equal to C, right? If this happens, then this means your T is surjective, right? Because that means your T of x will give you everything in the other Fm there, right? So you let x run through the entire Fn, and then you're going to get everything in the Fm there, right? So this is if and only if statement by the definition of T is surjective, and so that means the range of T, the range of T is equal to the entire Fm. And so that means the dimension of the range T is equal to M. If the dimension is equal to M, then good, right? Then this is, yes, so every C there, you can find one. However, if, let's consider the case if the N is less than M, all right? If N is less than M, then what, right? Then consider the case where we get the dimension of the V there, this is the Fn there, is the dimension of the null T, plus the dimension of the range T. So then this tells us the dimension of the range T is equal to the dimension of Fn, which is N, minus the dimension of range T is this, minus the dimension of null T. Okay. Minus the dimension of, let's see, we want the, if the N is less than M, right? So that's the right condition. We're trying to say this not the surjective. We can do the corollary, but I believe we will be also able to do this just by the fundamental theorem formula here. So null T, so this tells you the dimension of the range T is equal to the N. So then null T can be 0 or can be bigger. So this is less than or equal to N here, right? But the N is strictly less than M. So that's kind of same as our argument for the previous corollary 2 there. And so, but this is equal to the dimension of the Fm, right? So then this tells you the dimension is strictly less than that, so that tells you the range T is not equal to Fm. So then this tells you the T is not surjective, right? So T is not surjective means there's some W, generally from, if T from V to W, there's some W there, there's no V. Give you that W. So in this, putting into the vector context, that means there's some C there in the Fm such that no X give you the Tx equal to that C. All right. So in other words, if we put this in a plain language here, that says an inhomogeneous, because unless you know the C equal to 0, otherwise, generally speaking, it's an inhomogeneous system of linear equations in which there are more equations than variables, because there are m equations n variables. So m bigger than n means the number of the equations bigger than the number of the variables. All right. So if we have a system, there are more equations than the variables, then this system has no solution, all right, for some choice of the constant term. All right. For some c, there is no solution. All right, but we're not saying for every constant terms you put on the right hand side there is no solution. No, all right, but there must be something there or make that no solution. Or maybe there are one, maybe there are two, maybe there are several. All right, so for instance, if we consider something like x1 minus x2 plus x3 is equal to 5, yeah, well, no, we should not put straight number c1. All right, and then maybe it's probably a little bit easier to do something like this. Maybe let's put x1 plus x2 is equal to c1, or x1 plus 2x2 is equal to, what is the other one? x1 plus 2x2 is equal to c2, and then x1 minus x2 is equal to c3, right? So then this one tells you there for some c1, c2, c3, or for some c1, c2, c3, or this system has no solution. All right, we're not saying for everyone, right? For instance, if you put c1, c2, c3 equal to, I think 130, then actually there is a solution, right? Because if you take x1, x2 equal to 1, then you can actually make the first equation. If c1, c2, c3 is 230, then you can know that when x1 equal to x2 equal to 1, there is a solution, right? But on the other side, if you put like a c1, c2, c3, they all equal to 0, well, then there's no solution, right? Because it's pretty clearly if we put all of them equal to 0, then you have to get the well, no, not all equal to 0, right? If we put the first one equal to 0, the third one equal to 0, and then the second one equal to a non-zero number, right? Because the first and the second one, if they both equal to 0, then the only solution to that is x1, x2 equal to 0. If you put the second and c2 is non-zero, like a 5 or something, there's no solution, right? So, but what we're saying is not always no solution, but at least there is a choice for those c1, c2, c3, such that no solution, the system is inconsistent. All right, so that is the connection between our corollaries with some fundamental problems we asked in the linear algebra before, right? If T or if a matrix equation or there M system of equations M, which is the variables, is there are n variables, right? M equations, right? When m bigger than n or n bigger than m, what we can say. All right, so these are the two things we can certainly say what happens in each case, m bigger than n or m less than n. All right, so let's conclude the everything in the section 3, I think 3b here. It's a long section, or I try to give as much explanation as I can. So, but there are still some details I need to fill in. For instance, I skipped some proofs, and sometimes I just said something not write down. So make sure when you read a book like this, that's not a big book, but there every step there needs to be some explanation. All right, thanks for watching. So in the next recording, we're going to begin the next section. I think it's a 3C there. All right, see you there.